Hi, I'm Ben-Yaakov. The title of this presentation is The High Frequency Transformer Facts You May Have Missed. The outline is as follows. First, I'll give some introduction to the basic operation of a transformer, and then we'll discuss the cases of a short circuit, DC current injection, and related to it is the half-wave rectification and asymmetrical half-bridge PWM converter. I'll talk about air gap, whether it's needed in a transformer, and then how to choose the wire size, and finally say a few words about flat magnetic core. Now let me start off with the very basic relationship of a transformer. A transformer is built around a core which will be of a ferromagnetic material. And here is one winding on the core. We are imposing some voltage on this winding, and which has N1 turns. According to Faraday's law, the relationship between the voltage and the rate of change of the magnetic flux in the core, here it is, this magnetic flux, is related by this equation, from which we can find that the rate of change of the flux is V over N. So if we impose a voltage on a winding, phi will increase according to this relationship. Now if V is DC, then phi will go up and up because the integral is sort of a straight line, and this is why you have to use AC voltage only, and if you impose a DC voltage, then the phi will sort of go to infinity. B is related, B is the flux density, is related to phi, to the flux, by this equation, flux over cross-section area of the core. Cross-section area of the core is here. This is cross-section area, and which is a similar relationship, except that, of course, it is divided by A. So if we impose a sinusoidal waveform like this, then phi will be like a cosine, actually minus cosine. It'll be like this. It'll be sort of shifted 90 degrees. And if we impose a square wave, like here, then phi will go up and down, up because this is a positive slope, and down because it's a negative slope. In steady state, it probably stabilize to be symmetrical, so this will be the change of flux, and also this is how B will look, except that there is some constant between them. If we have a square wave voltage, then phi and B will be sort of triangle, and since during this time V is sort of constant, so during delta t it's constant, and it'll sort of increase phi, and B will increase linearly. It'll be a linear function of time. Now, practical ferromagnetic materials do have a saturation phenomenon. That is, the curve between B and H shows here sort of a flatness here, and this is actually an area in which the ferromagnetic material loses the ferromagnetic behavior. So you would like to stay within this line. Now, you usually define a given B max that you like to reach, and I'll talk about it in a minute. This will be the B saturation. You certainly wouldn't like to get to this point, but you like to get to a lower point. So B will also increase linearly, and we find from here that N times AE should be actually larger, larger than V delta T V max. V delta T is actually the volt second accumulated during the pulse time, and B maximum is the allowed B that you like not to exceed. This equation is really very interesting because it says that you can trade cross-section area, here's the cross-section area of the core, by number of turns. That is, you can have many turns in a small area or a large area with fewer turns. Now let's go back to the question of how do you set Bmax? Well, at high frequency, the limitation will be actually related to core losses. That is heating up of the core. And the core losses are a function of delta B. That is the span of B during operation. This is delta B. And a function also of frequency. The higher the frequency, the larger the losses. A typical relationship is shown here. This is a curve that you'll find at the manufacturers of cores, which shows the core loss usually in watts or milliwatts per centimeter cube, or sometimes per gram, as a function of this delta B. As one can, this is actually in a log scale, and this will be for one frequency, this will be for another frequency. So if your delta B is, let's say, like here, then for F1, which is a lower frequency than F2, these will be the losses, and for F2, these will be the losses. So once you choose the operating frequency, you set a limit actually on delta B, considering the heat dissipation that you allow from the core, and this actually set the Bmax, which is actually this value here. Now we go to the question of the inductance that we see when you look into a winding. An ideal transformer should have an inductance which is infinitely large. That is, it's like an open circuit, you might say. In reality, you see inductance, of course, and the value is the value described by this equation. This is the number of turns. A is the core cross-section area. Mu is the permeability, which is mu 0 times mu r. Mu r is the relative permeability. And Le is the magnetic path length. A is, again, the area. If you have some inductance, then as you impose a voltage, you are going to see a current, a change of current. And for a constant voltage, at least for a given period of time, T on, the delta I will be this value. So obviously, when the inductance is low, delta I will be large, and this is sort of a waste because there's some circulating current here that you really don't need. So this is why you like L to be as large as possible. Now, to make L large, you, of course, can use a core with a larger cross-section area, larger number of turns, and mu, which is large. Now, ferromagnetic materials do have a relative permeability, mu r, in the area of, say, 2,000 to 4,000, and this gives them the efficiency as a core for a transformer, because then the inductance will be really high. You can arrive at this delta I in a different way, which is shown here. I'm not going to go over it. You can just stop the video and just have a look at it. Now we are coming to the question of the voltage ratio between two windings. We have N1 and then we have N2. According to Faraday's law, V is related to the rate of change of the flux by this equation. Now, this will be, of course, correct for the other winding. Now, since they are wound on the same core, and we assume that all the flux is passing through these two, that this little flux is sort of the so-called leakage inductance. Most of the flux is really shared by the two winding. So by dividing these two equations, we are getting the very familiar relationship between V1 over V2 is equal to N1 over N. Now the dots actually signify the polarity. So they mean that if you have plus here and minus here, you'll find also plus here and minus T. This is the meaning of this dot. What will happen if we are going to impose a voltage VI, say sinusoidal of a sinusoidal waveform and load the second winding with a resistor R. Okay, the question is, what will happen to the currents? Now, obviously, since the R sees a positive voltage here and a negative voltage here, then the current here will be this way. Now, what will be the current here? Well, there are two ways to look at it. One is based on energy conservation, which says that since you have power coming out here, you must have power going into the winding so that the two will be equal, so that you'll have V1 I1 is V2 over times I2, and since V1 and V2 are related by the turns ratio, then you'll find that N1 I1 is N2 I2. Well, this explanation is really not very good because we do have cores with two windings or more in which this does not hold, okay? So a better way to explain the case of a transformer is to say the following. If we have a load here, then no question there's going to be a current, and the current will be V2 over R. As we have the current flowing, the current will initiate a magnetic field into the core. The relationship, should be LE here. Therefore, there will be a change of flux, which is related to the magnetic field. Therefore, it's going to be a change in flux density, and therefore, it's going to be a change in the flux. If there is a change in the flux, while we still impose a voltage on V1, then the only remedy to correct the flux to be according to Faraday's law is for a current to flow and sort of correct and remedy the change in flux and bring it back to the value according to Faraday's law. This is actually a variation, what I'm saying, of Lenz's law. So this would mean that if current is coming out from the dot in one winding, it'll go into the dot in the other winding, so that the effect of N1 I1 is canceling N2 I2 by the virtue of being of the same magnitude and opposite directions. Now let me move to examine various cases that we are going to talk about. There is a feeling that if we are going to have a short in one of the windings, while still imposing a voltage here, we're going to have a saturation of the core. Well, this is not the case, because what will happen really is that the current will go up and up. Phi is not going to change. That is, we are not going to move into saturation, but rather the current will go up, and eventually, of course, there will be overheat of the windings, and the system will stabilize, well, before smoke, at a point in which the voltage drop on this parasitic resistance will be equal to the input voltage, so that there will be very little voltage across the winding, and that will be the end of it. But then at that point there will be a large current flowing here and a very large current flowing here, so actually we are in danger of damaging the wires. So this is actually what will happen, and the core is not going into saturation. Another question that I like to pose here is, what happens if, in addition to the voltage excitation, I'll add some DC current to the core? The AC excitation is moving the B, flux density, up and down, depending on the value of the voltage. And when adding some DC current, the whole line will go up. That is, if I look at B as a function of time, say, without the DC current, it'll move like this, and then with the DC current, it'll be like this. This is B, and this is time. Now, what about the effect on the second winding? Well, there is no effect, because if it is a DC current, then the phi resulting from it is constant. There is no d phi dt, so therefore there actually no change in voltage. This situation of DC is found in some applications, or some cases. For example, if you have a transformer, which is shown here, and you have a halfway rectifier, which causes current to be of this shape, this will cause a current of this shape here with a certain average, and this is a case of a DC current through a transformer. The second winding will not be affected by it, but if the DC current is going up and up and up, then it might bring the core into saturation. This is something which is really highly undesirable. There are other cases in which you have this situation. I show here, for example, a DC to DC converter, which is called a asymmetrical half-bridge PWM converter. The principle is similar to the regular PWM, but there is some asymmetry. That is, the transistors are not operating in a symmetrical way. One is turned on for a shorter time, the other one is turned on a longer time. This will cause of asymmetry in the voltage here, asymmetry at the output, and what will happen then, that the diode conduction time will be different, and assuming a large filter capacitor, then you'll see currents in half of the windings like shown here. Obviously, the average here is, say, here, and the average here, so that we have two currents, but they are unequal, and therefore there is actually a DC current flowing in the secondary. Now, the reason for using this type of a converter is because you can achieve here zero voltage switching, which I'm not going into. It improves or reduces switching losses, so the system can be operated at a fairly high frequency. So what can you do? The problem that you are facing is that if this current is just too high, then you will move into saturation because of the extra current. So the way to remedy this is actually to introduce a gap into the core, like we do in inductors. What is the gap actually doing? The gap is sort of lowering the permeability. Instead of having the original permeability, we have a lower permeability. So for a given magnetic field strength, instead of being in saturation, the lower permeability will actually maintain the system into a reasonable flux density region. The required relative permeability needed is related to by this approximate equation. Now, what's the downside of this is that number one, L, that is the inductance, which is a function of mu, will become lower. So we'll have a higher magnetization current. Another problem that might arise is that the lower permeability may cause larger leakage inductances, which is not desirable, and again, this is not a subject that I'm going into in this presentation. Now, what about the wire size? Wire size depends on the resistance that you'll have, and that is, you like to choose a wire such that the heating and the thermal dissipation will be in the range that is acceptable in your design. Once you know the number of turns that you have, you can calculate the total length, and knowing the diameter and the material, which usually will be copper, you can calculate the total resistance, and knowing the RMS current, you know what is the power loss. At high frequency, one has to take into account that there is a skin effect, meaning that the charge is sort of accumulating at the outside part of the cross-section, and therefore the effective area becoming smaller, so that at very high frequencies, if you need a heavy wire, you cannot use it. You'd rather use a Litz wire, which is a bundle of smaller wires such that the total cross area is the one that you need, but each one, they have to be, of course, isolated from one from another, and the cross area of this one and the diameter will comply with the skin effect phenomena. Now here, taking from Wikipedia, I've brought the skin effect depth as a function of frequency for a number of materials. Here is copper. This is the copper. So we see that at 100 kilohertz, the skin depth is, say 0.2 millimeter. This would say that if you have a wire and this is the diameter, then the charge will concentrate at a thickness of 0.2 millimeter. So if you use a 0.4 millimeter wire, it'll be sort of completely full with the charges. But if the cross-section, or if the diameter will be larger than 0.4, it will be larger than 0.4, then you'll have this effect that the actual utilization of the wire is much smaller than the diameter. Consequently, you'll have a resistance, which you call it RAC resistance, which will be larger than RDC resistance, that is the resistance of the wire at very low frequency. So this is a consideration that you must take into account. Finally, I come to the subject of flat magnetics. Now, flat magnetics stands for shapes of core which are sort of different from the one that I've sort of shown before, and that is they are characterized by large AE, this will be the cross-section here, right, and a much smaller winding window. Therefore, it actually trades the winding window with the cross-section area of the core. It turns out that this product, the AP product as we call it, AE over AW, is a measure of the core that you need. You can calculate it from the parameters that you know about the operation of the transformer, like voltages, currents, frequency, etc. So in the case of flat magnetics, the winding area is traded for a larger cross-section area of the core. So it's be a heavy core and much fewer windings. There are some advantages to it, as I'll explain in a second, but let's see what it really means. It means that you have less windings, so you have lower copper or wire winding losses. You have a larger core, so you have a larger core losses because the loss is a function of the volume of the core. However, it's easy or relatively easy to cool the core by clamping it to a heatsink, say, and therefore you can remove the heat fairly easily. Furthermore, an important feature here that you can use a printed circuit wire or winding which are very thin and therefore very efficient at high frequency because they could be thinner than the skin depth, and you can stack them to get the number of windings that you need, and by this it becomes more efficient packing of the winding into the winding area. The downside of these flat magnetics transformer is that there is a much larger interwinding capacitance because the close proximity of the windings one to the other and the large area that you have in here. However, flat magnetics are really very useful at very high frequencies, and they are really now becoming very popular. This actually brings me to the end of this presentation. I thank you for your attention. I hope you'll find it useful in the future. Thank you.